and I'm very glad to be able to present a very recent work that was submitted recently to ANA, mostly in collaboration with Marco Padovani and Daniele Galli in Italy, but with Birbo Jeric in Croatia and Elena Bellomi in France, not forgetting all the people working in LOFAR on the LOFAR data, and in particular to Luca, who just presented his work, and the work of another PhD student here in Croatia by Anna Herzeg, who basically produced the beautiful images I'm going to show you, like the one you see in the background. Okay, so what we're trying to do is really trying to understand what's going on once we look at such data set. So here you're seeing data from the LOFAR telescope at very low frequency, 150 megahertz. And this is a huge mosaic over tens of degrees in the sky. You can see in celestial coordinates. And here there are two elements that I want to focus on. One is the grayscale. It's polarized emission from synchrotron radiation at very low frequencies. And the other one is this changing number on the top right, that is the amount of Faraday depth. So we're seeing the polarized intensity changing while the Faraday depth is changing. Now, I don't have time to go into the details of Faraday rotation. Luca mentioned something. It was already mentioned before. Somehow the process. The point here is that Faraday rotation involves ionized and magnetized interstellar gas along the line of sight. And something, sorry, that the LOFAR data are revealing, as Luca just said and highlighted, is the strong correlation, though, between Faraday rotated polarized emission detected by LOFAR and traces of the neutral medium as probed by dust in H1 at 21 centimeter. So the question is LOFAR actually a new window that allows us to look at the multi-phase and magnetized interstellar medium? And this is really the real avenue and prospect that we have in mind. But in order to do so, we need to develop models that are able to capture the complexity of this data set. And as I said before, it's a matter of modeling polarized emission of synchrotron emission that is including cosmic ray electrons and magnetic fields on one hand. On the other hand, the process of Faraday rotation that is including thermal electrons, so the ionization in interstellar medium and magnetic fields itself. Now, the present work I'm gonna talk about is really focusing on the first part, on the basics of synchrotron emission. In particular, a fraction of the polarized, so the polarized emission is actually a fraction of the total power. Here visualized in proxy of brightness temperature of synchrotron, that is usually thought and observed actually to be somehow a power law of the frequency. And this spectral index of this power law is observed to change both in frequency space, but also over the sky. Okay, and these changes must be related to changes in the synchrotron emissivity. And in particular, I want to focus on one contribution to the synchrotron emissivity, that is the synchrotron energy spectrum. Okay, usually this synchrotron energy spectrum is assumed to be again a power law of the energy of the cosmic ray electrons, that is either a single power law of -2 or -3, depending on the energy of the cosmic ray electrons that are responsible for synchrotron emission. And this contributes to the single power laws of beta, the spectral index beta I was talking about. Now, in practice, very recent observations are showing that, here you see a compilation of different data sets. You can see that this energy spectrum is actually variable as a function of energy. And indeed, maybe if we are focusing at low energy or at very high energy, the assumption of using one single power law then is valid. However, what happens if we fall exactly in the knee of these energy spectrum. And this is what we asked ourselves. And in practice, we used these actual observations as a template of the energy spectrum, and we plugged into the equations, and we estimated what would be the spectral slope of the cosmic ray energy spectrum for different energy, for different observational frequencies. You can see between 100 megahertz and 10 gigahertz, and different magnetic field strength that one could expect in the diffuse interstellar medium that we may find at intermediate high galactic latitudes between 2 and 20, between a few to tens of microgauss. And you can see that mostly at low frequencies, those that are interesting for LOFAR, the assumption of a single power lobe, of a single spectral slope for the energy spectrum of the cosmic ray electrons breaks down. Okay, here shown by the green plot. In practice, actually, a constant spectral slope may be valid at high frequency in certain conditions. However, we also show that even at high frequency, depending on the ISM structure along the line of sight that we see, well, the assumption of a single spectral slope may be too strict of a constraint in modeling and understanding synchrotron emission. Okay. So this is really the main message of this work, that in order to model synchrotron emission at low frequency, possibly a variable spectral index of the cosmic ray energy spectrum must be considered. Okay, and this is what we tried to do then, using MHD simulations as a proxy of what we see in the diffuse and magnetized interstellar medium. In particular, we're interested into exploring the relation between different phases in the ISM. And so we used state-of-the-art simulations of the multi-phase neutral ISM, where there is thermal instability, and it's a turbulence in a box simulations. Okay, from these simulations, we can
3 minutes.
Yes, we can derive an emissivity from which, given the energy spectrum that I showed you before, we can derive a brightness temperature and thus derive variations of the spectral index of the synchrotron brightness temperature as a function of frequency at very low frequency. I mean, in the frequencies typical of LOFAR. This is what we get. Long story short, you can see two different diagrams corresponding to different initial magnetic field strength of the simulations. And you can see here these 2D diagrams that show the distributions of the spectral index also as a function of these turbulent to mean magnetic field parameter in the simulations. Basically, what I want to highlight here is that depending on the ISM structure that we happen to see in these specific simulations, but I guess in general in observations, the values of the spectral indices may significantly vary, and mostly can be mostly different from the typical values of -2.5 that one would expect, assigning as a fixed cosmic ray electron energy spectrum, as most of the models, mostly for computational reasons, are doing today. Finally, I want to show an idea that we propose, in which basically, given the range in frequencies that we observe and the observed spectral index that one would observe in these frequency range, we could give a rough estimate, actually, of the average plane of the sky magnetic field component along the line of sight. And this may be useful given the upcoming upgrades of LOFAR, for example, but also with the SK telescope coming online. So it could be, in any case, just a new hint of what's the strength of the magnetic field along the line of sight. Well, on the plane of the sky magnetic field, but average along the line of sight. And with that, I really conclude. And I want to stress that the complexity of the LOFAR data requires new models and Dorf models to understand what we're seeing. We're seeing a composition of synchrotron emission and farther rotation. And what we are trying to propose in this work is really that at these low frequencies, in order to model correctly the synchrotron emission, we need to consider variable cosmic ray energy spectrum. And the next step, would be to introduce the complexity of farther rotation. And for that, we need to face another challenge, that of introducing the ionization processes in the interstellar medium and put together the pieces of the ionized gas and neutral gas. With that, I conclude, and I thank you all for your attention.